Okay, so this is like part two of the set of notes that are on parallel lines. Last time around, we talked about using parallel lines to prove angles congruent. Now we're going to be proving lines parallel. Okay, so basically, this is the converse of everything that we did last time around. So last time around, we had this idea, like if I have the drawing and I've showed, and I have the parallel lines, then I know that the corresponding angles are congruent. So the converse to this, so this is going to be the converse to the corresponding angles postulate. So this one's a postulate. You don't have to actually prove this one. The converse to this one is that if in fact you get two lines that have congruent corresponding angles, so congruent corresponding angles, in fact prove that the lines are parallel. Okay, so that's one, right? Last time we got that if I have parallel lines, then the alternate interior angles are congruent. The converse here of the alternate interior angles theorem is actually going to state this the other way around. If I have congruent alternate interior angles, you're going to see a theme here, then the lines are parallel. We also got an alternate exterior angles theorem that said if the lines are parallel, then the alternate exterior angles are congruent. Here we get a converse to that. So if I have congruent alternate exterior angles, right, then the lines are parallel. Okay, so there's a couple more things that we need from this set, and we'll keep going here. Okay, the oddball in the set is to say that if I have two parallel lines and the same side interior angles are not congruent, they are supplementary, they add up to 180, then, well, if they're parallel, then these two angles have to add up to 180. So we get a converse of that, right? So this is the converse of the same side interior angles theorem. And in this case, if the same side interior angles are supplementary, then the lines are parallel. Okay. Now, we have a couple more things that we can kind of tick off here. We get a theorem which we're going to prove at some point along the line in class here, that if in a plane, if you have two lines that are perpendicular to the same line, then they're parallel. This is basically a corollary of this, because if that's 90 and that's 90, then they're supplementary, which means the lines are parallel. Okay, so two lines perpendicular to the same line in the plane have to be parallel. We get this odd thing in a minute that's somewhat disputed in mathematics, a little bit of controversy here, but for our sake in our class, we're going to accept it. This is what we're going to refer to as Euclid's parallel postulate. So this is a named postulate. Euclid had the idea that if you have a line and a point not on that line, then there exists exactly one line in the plane that is parallel to the other line. Now, this is the odd thing. This postulate only holds in the way that we are envisioning a point, a line, and a plane. In some other forms of geometry, this does not work. And this leads us much later in mathematics to things that are called non-Euclidean geometries, which are outside the scope of this course. This course is completely about Euclidean geometry, but it's important to kind of note that this does exist, and we got a little controversy in mathematics here as to whether or not this is actually true in all cases, and it turns out that it isn't, but for our sakes, we're going to hold it as an accepted statement. There's also another postulate here that if I have 2 points, let's call them A and B, you can only draw exactly one line through those points. So this is like the idea that 2 points determine one line. We're going to need that postulate for some other things in this class. Okay, so this brings me to 2 more unnamed theorems. One theorem states that if I have a line and I have a point not on that line, then there exists exactly one line that is perpendicular to the original line, so that that line is unique. This theorem is a direct result of Euclid's parallel postulate. We're not going to prove this in this class. It's a bit subtle and a little more complicated than we would like to imagine, but it seems pretty clear that if I have it going through this point and I make it perpendicular, I'm going to only be able to do that one way. And the last one is a theorem that we will prove. It says that if I have 3 lines and I have these 2 being parallel and I have these 2 being, sorry, it's not true, those 2 being parallel and these 2 being parallel, so 1 and 3 are parallel, 1 and 2 are parallel, then it follows that this one and this one also have to be parallel. So if 2 out of the 3 lines are parallel, all 3 have to be parallel. And that one we're actually going to prove here. It's pretty straightforward, but we should acknowledge that it can be proven, and we will. Alright, so for the proof of that, I'm going to create 3 lines. I'm going to call this one K, I'm going to call this one L, and I'm going to call this one N. Okay, and we're going to be given that K is parallel to L, and that K is parallel to N. And we want to prove that this means that L is parallel to N. So the way to do this, given what we have, is to actually create another line here. So we're going to create a line here. We're going to call that T because it's a transversal. And we're going to number some angles. We're going to call this one number 1. We're going to call that number 2. And we're going to call that one number 3. And we're going to make some statements. And we're going to make some reasons. Alright, so right off the bat, we have that K is parallel to L, and K is parallel to N, and that's given to us. Woohoo! That's not earth-shattering, right? But because K is parallel to L, 1 and 2 have to be congruent. Angle 1 has to be congruent to angle 2 because they are alternate interior angles. So I'm using the alternate interior angle theorem to do that. Now note, because K and N are parallel, 1 and 3 excuse me, are also congruent because they too are alternate interior angles. So I'm going to get 2 for 1 here. I'm going to say that 1 is congruent to angle 3. Actually, I'm going to be a little more clever about this. I'm going to say that angle 3 is congruent to angle, nope, sorry. Yeah, angle 3 is congruent to angle 1. Alright, so this way I don't have to use a symmetric property later on. Alright, so let's see. If 1 is congruent to 2 and 3 is congruent to 1, then angle 3 has to be congruent to angle 2. And that's by the transitive property. Right? If A is congruent to B, and B is congruent to C, then A is congruent to C. So that's got to be true. But see, 3 here is in the same position as 2. So these are corresponding angles. And the corresponding angles formed by L, N, and T, which means that L must be parallel to N. And this is by the converse of corresponding angles postulate, which we stated earlier in this video. That if the two corresponding angles are congruent and the lines lie in the same plane, then the lines have to be parallel. All right, so we've just kind of done some work here where we took all of the things that we said that if we have parallel lines, then we get congruent angles. And we've stated that all of those converses are also true. So ultimately, we get that if I get these bunches of angles, then I also get congruent lines. So if the alternate are not congruent lines, parallel lines. So if the corresponding angles, alternate interior angles, or alternate exterior angles are congruent, then the lines are parallel. If the same side interior angles are supplementary, the lines are parallel. If they're both perpendicular to the same line, then they're parallel. And if you have two lines that are parallel to the same line, then all three lines are all parallel to each other. All right, so that's our message for today.